Okay, Chapter 1, Section 5, Solving Quadratic Equations. So in this section, we're going to look at solving quadratic equations by factoring, solving quadratic equations by completing the square. We'll explain what that means. Using the quadratic formula and also deriving the quadratic formula. We're going to talk about the discriminant, and then we're going to do modeling with quadratic equations, which just means a word problem. Okay, so first of all, what is a quadratic equation? So a quadratic function is a polynomial function of degree 2. So a quadratic function is of the form ax squared plus bx plus c. This is where the a, the b, and the c are constants. So don't forget, there's a lot of letters running around here, but the only independent variable we have here is the x. So this is a function written in x as the independent variable. And the other constants, the a, the b, and the c, the other variables represent constants. A, b, and c represent numbers. And this is where a is not allowed to be 0, simply because if you let it be 0, then you get rid of the term that has an x squared, and then you no longer have a quadratic. Okay, so for example, we could look at functions that fit this form. So f of x could be equal to 7x squared plus 2x plus 5, right away, that looks exactly like this. The a is a 7, the b is a 2, the c is a 5, right? Or another example, f of x, okay, so the constants could be anything, could be negative, so like negative 8x squared. It could be a decimal, 0.5x. Or it could be a fraction. Maybe the c is 11/3. Right, so here's another example of a quadratic. Also, it could be a quadratic sort of in disguise, something that requires a little bit of algebraic manipulation to get you there. So for example, you could have something that fits this form. Maybe it's like x times x plus 2 plus 7. Right, so it doesn't quite look like that, but I know that after just a little bit of work, I can make it fit that. So if I distribute this x, right, if I distribute this x here and then there, then I know that that ends up with an x squared. So at that point, we end up with f of x equals to x squared plus 2x plus 7. And now it fits that form right there. Okay, but just like in lines, there's more than one way to represent a line, right? So we learned that, for example, there's the standard form that fits this. This is ax plus b y plus c equals 0. This was the standard form of a linear equation. For example, something that looks like this would be like 3x plus 5y plus 7 equals 0. So here is a line in standard form. We also learned the slope-intercept form, y equals to mx plus b, right? So for example, something that fits this form could be y equals to 3x plus 7, right? And finally, there's the point slope form. So it's like y minus y1 equals to m times x minus x sub 1. Right, and again, something that fits this form could be something written like this: y minus 2 equals to 11/5 x minus 3. Okay, all right, so there's 3 different ways in which we can express lines. Let's put this over here. These are lines. Learned that before. And using our algebra skills, we can always go back and forth between these. Right, so I can use some algebra skills to rewrite this one and make it fit this form, or I can make it fit this form, right? So this is in standard form, but I can make it fit slope-intercept form by solving for y, or I can make it fit this form, right? Likewise with this one, I can make it fit this form, or I can make it fit this form, and so on and so forth. So there's different ways to express lines, but they're all lines. And there's advantages and disadvantages to each of these. Depending on what you're doing and what you want to accomplish, one form might be better than another form. Okay, likewise with quadratic equations, this is the standard one. This is the standard polynomial form of a quadratic equation, but there is another form called the vertex form. Okay, so a quadratic function of the form ax squared plus bx plus c, right? This is the standard polynomial form right here. This can be written, can be expressed using a process called completing the square. So we'll talk about that soon. But we can use an algebraic process to manipulate this one to make it look like this, and forwards and backwards. So it's called the vertex form of a quadratic equation. And the advantage of this one is that we can easily tell some things about the graph, right? So the graph of any quadratic is going to look like this. Hopefully that sounds familiar. It's a parabola. It's like a giant U. It either opens up or opens down. That's a parabola. And then the tip is called the vertex. Right, so right here, we call this the vertex of our parabola. This one opens up. And this one opens down. It's a parabola that opens down, and the vertex is right there. And as you can tell from our formula, the vertex is h comma k in either way. So h representing the value of x, k representing the value of y. And if we look up at our vertex form of a quadratic, we see that the h is right here and the k is right there. So similar to lines, when we look at this form, y equals mx plus b, we can spot the slope right in our equation, right? Here's our slope. And we can spot the y-intercept right there, right? The y-intercept is 0 comma b. So there's a really nice advantage to writing an equation of a line in this format. So if someone, for example, gives you the line 3x plus 6y equals 4, let's say 5, and they ask you to find the slope, okay? Well, this is not written in this form, but we can solve for y quite easily. 6y equals to negative 3x plus 5, divide everything by 6. Y equals to negative 3, 6x plus 5 over 6. And so y equals to negative 1/2 x plus 5 over 6. And now we can easily spot the slope. Slope, right there, right? So likewise, we can go forwards and backwards with quadratic equations that either fit this form or the ones that fit this form. And the advantage of working or looking at a vertex, a quadratic equation in this vertex form is that we can easily spot where the vertex is because of the h and the k. Okay. So, for example, something that's written this way, f of x equals to, say, 3 parentheses x minus 5 squared plus 8. This fits the vertex form, right? And from here, I can tell that the vertex this fits the quadratic, the vertex form of a quadratic. So this fits the vertex form of a quadratic, and we can tell from here that this, comma this, is going to be our vertex. Vertex at 5, 8. Okay, so we can use algebra to go back and forth. So for example, back to the standard form, if f of x was equal to so we can go forwards and backwards with the standard form and the vertex form. So now if we wanted to express this exact same thing in the standard form, all we have to do is FOIL this out and expand it, combine like terms. So expanding this gives you an x squared minus a 10x plus 25 plus 8. Now we distribute that 3, and we get 3x squared minus 30x plus 75 plus 8. And so now we just combine this 75 over here. And so we end up with 3x squared minus 30x plus 83, right? So now this fits the standard form, right? So we've gone from the vertex form, and then do a little bit of algebra, and we end up with the standard form. So from the vertex form, we were able to easily spot where that vertex is at 5, 8. But from the standard form, that's not as easy. We could still do it. It just takes a little bit of work. But very often what we have to do is start with something that looks like this and go backwards so that we can find the vertex, right? Just like in lines, sometimes they give you something in standard form. Right? And then if you want to find the slope, it makes sense to do this work to rewrite it into the slope-intercept form. Slope-intercept. And then you can easily spot the slope right there, right out of our equation. So likewise, sometimes we're given a quadratic in this standard form, and if they want us to find the vertex, which is a very common thing to do, then we might have to do the work it takes to go this way to rewrite it like this. To go in this direction, we have to do a process called completing the square. Okay, so we'll do one of those in a little bit. For now, let's move on to solving quadratic equations. And, well, there are, depending on the equation format that's given to you, sometimes it's a pretty easy process. Sometimes it could be a little bit more work. So let's look at one type of example. Okay, so solving quadratic equations by factoring, when factoring is possible. Okay, so we're going to take advantage of this property. So some quadratic equations can be solved by factoring and using the following basic property, the zero product property. The zero product property states that if a times b equals to 0, then it must be true that either a is 0 or b is 0. AB equals to 0 if and only if a is 0 or b is 0. Notice, very importantly, that this is multiplication. So this is saying that if we have two numbers and we know that when you multiply those two numbers, the answer is 0, then at least one or maybe both are 0, right? So I have blank times blank, and I know the answer is 0, then this tells me that I know that either this one is 0 or this one is 0, right? That's a special property of the number 0 in our number system. It's the only number that has this property. People often think 1 also has that property, but it's not true. So, for example, if I know two things are being multiplied and the answer is 1, then I cannot conclude that one of them is a 1, right? There's a lot of things that multiply. There's a lot of ways to get two numbers that multiply to the number 1. There's 1/4 times 4, that equals to 1, right? And neither one of these terms is a 1, right? 1/4 times 1, for instance. Now you can do it by multiplying 1 times 1, which equals 1. So it is possible to say one of them is a 1 or both of them is a 1, but it's not required. It's not guaranteed. Whereas with 0, it is guaranteed. If two numbers are being multiplied and the answer is 0, the only way to make this a true statement is if at least one of them is 0. There's no way to get two numbers that are both non-zero and the answer is 0, right? So that's a special property of 0 in our number system, the zero product property. Now, this requires multiplication though, because if we have addition or subtraction, then again, that's not true. If I have two numbers that are being summed, we're adding two different numbers and the answer is 0, I cannot conclude that at least one of them is 0, right? Lots of different ways to get two non-zero numbers to add up to 0, but -3 and +3, for instance. Neither one is 0 and they add up to 0, right? So with addition, it doesn't work, only with multiplication. So this makes it very useful when we have, say, for example, unknown values, x plus 1 and say y. And if we know, for some reason, that the multiplication of these two things is equal to 0, then we can separate this into two separate little questions because we know that either this term is 0 or this term is 0. So we can separate it as x plus 1 must be the 0 or y is 0. And so we can solve for x must be a 1 or y must be a 0. Good. Okay, so we use this property whenever we can rewrite our statement as a multiplication that equals 0, right? So that's another thing that people often mess up. They use the zero product property, but they don't set the right-hand side equal to 0. So let's look at an example. For example, let's say that we wanted to solve this quadratic equation. Obviously, we know it's a quadratic equation because it's a degree 2, right? That's how we know it's a quadratic. It's only got one variable. The variable is x, and it's a degree 2, so we know it's a quadratic. And we can easily rewrite it into the standard form. So if I just move this 24 over, I can rewrite it as x squared plus 5x minus 24, equals 0. And now this fits the standard form of ax squared plus, let's use lowercase. Ax squared plus bx plus c equals to 0, where the a is a 1, this invisible 1 out in here, the b is a 5, and the c is negative 24. A equal to 1, b equal to 5, and c equal to negative 24. So it fits the standard form. Okay, so one way to solve this, one way to figure this out is to factor this, and if it factors nicely, then the problem won't be too bad. If it doesn't factor nicely, well, then we're in trouble, and we might have to do something else, try something else. Okay, so this is a trinomial, degree 2. The leading coefficient is 1. So one thing we could try is see if this works, right? Guessing and checking, trial and error. We're going to try this. X times x gives me x squared. And then what I'm looking for is for two numbers that multiply to negative 24 but add to positive 5. So we can just kind of play around with the different values. There's obviously, say, 12 and 2. They multiply to 24, but they're not going to add the 5 in any way. 14 or 12, depending on the signs. So that's not going to be it. How about 6 and 4? 6 and 4 multiply to 24, but they add to either 10 or negative 2, positive 2. It's not going to be anywhere near the 5. That's not going to work. 8 and 3. 8 and 3. They will multiply to 24, and there's a way to get them to be 5 if I add or subtract them. So I want a positive 5, so I'm going to make this a positive 8, and this a minus 3. Now that gives me negative 24 when I need it there, when I multiply them, and they add up to positive 5. Okay, so good. So we were able to factor it. This was a nice, easy quadratic to solve because we were able to factor it. And now we use the zero product property, right? We're saying that this is my A and this is my B, and I'm multiplying them, and the answer is 0. The zero product property tells us that at least one of them must be 0. So I get to separate this into two separate little questions. Either this is 0 or this is 0. Good. From here, I can just solve by subtracting 8 minus 8 minus 8. And so I end up with x equals to minus 8. From here, I can solve by adding 3 plus 3 plus 3. And so the answer is x equals to 3. X equals to 3. Okay, so I have two answers. And so we can always go back over here and check them. Check. Make sure that they work out. So if they work out, it must be true that blank squared plus 5 times blank equals to 24. And so one of them is going to be this minus 8. And minus 8 squared, that's going to be 64. Plus 5 times negative 8, that's negative 40. And yep, that does equal to 24. That worked out. Okay, what about the next one? So if the next one works out, then that must mean that blank squared plus 5 times blank equals 24. And this time we're going to check it against a 3. So you put a 3 there, put a 3 there. That gives us a 9 plus 15. And yep, that does equal 24. Good. Worked out. So I checked it, by the way, by going back to the original statement. Just in case I made a mistake from the original statement to there. Well, there I did move it over. In case I made a mistake there, then I would catch it, right? So if I made a mistake here, if I accidentally moved over the wrong way, maybe put a plus 24, and then therefore I factored it wrong, then I'll catch it. I'll catch that mistake. So meaning that if you check it here, assuming you did everything correct, you'll get a true statement. But if you made a mistake up here, you copied the wrong question, then when you check it, you're going to check it against your wrong question. So you're going to get, you're not going to spot that you made a mistake. So you should always check it by going back to the original statement is what I was trying to say. But if everything worked out well, then this would be a good way to check it as well. So to check it against this equation, for x equals to -8, let's put it over here. This is for x equals -8 over here, and this one is for x equals to 3. We should be able to replace this equation and get a true statement. So this one is saying that blank plus 8 times blank minus 3 is equal to 0. And so if we replace the blanks with a -8, -8, and -8, the answer will be true because this is going to be 0. This will not be 0. This will be -11. But -11 times 0, right? This is going to be 0 times -11, which is still equal to 0. Good. Okay, over here, if we replace the blank plus 8 and blank minus 3 equals 0. And then if we replace the x value with a 3, here we get a positive 11. But here we get a 3 minus 3, which is 0. So we end up with 11 times 0, which is 0. So again, it does work out. And here's your author's solution for this question. And it was basically the same thing I did. Move over the 24, factor it, and then you can use the zero product property to solve for both answers and then check them. Okay, solving quadratic equations by completing the square. So, completing the square. What do we mean by completing the square? So, in order to explain completing the square, I'm going to refresh your memory on some perfect square binomials. So, if you recall, if we multiplied x plus 2, let's start there, squared, then this is the same thing as x plus 2 times x plus 2. And then we can FOIL, O. And so we end up with x squared plus 4x plus 4, right? Combining the middle terms. Also, we solved this in general, and we saw that this was, if we had a plus b squared, we saw that this was a squared plus 2ab plus b squared. So we have that sort of general formula. Important note that there's a 2 in there. Okay, so if we had a few other ones, let's do x plus 3 squared. Instead of foiling it, I can just apply this formula. So there's going to be x squared for the outer term. The last term is the 3 squared. I usually like to skip over there and do 3 squared, right? Or 9. I'm just going to write it as a 9. 9. And then the middle is twice the two terms that you're squaring. So it'll be 2 times 9x. Oops, 2 times 3x. So it'll be 2 times 3x, which gives me x squared plus 6x plus 9. Pretty easy pattern, so it's easy to kind of skip this middle step and go right to that. But yes, x plus 3 squared equals this. Let's do just a couple more. x plus 4 squared equals x squared plus 8x plus 4. That's 4 squared, which is 16. X plus 5 squared equals to x squared plus 10x plus 25. Do one last one. X plus 6 parentheses squared equals to x squared plus 12x plus 36. Okay, some quick little patterns to notice real quick here. So the last term here, this one, 36, is this term squared, right? Obviously, this term is this term squared. But look at the middle one. The middle one is always twice as big as that one. So if we multiply this times 2, we get to that one. Or, likewise, if we divide this one divided, I'll use this notation, divide by 2, we get to that one, right? And that's because the constant in front is a 1, so it's just a pattern that works out nicely. This works out nicely when we only have a simple x value there, right? But it's always the case. 2 times 4 is 8. 2 times 3 is 6, right? That's how we get this. And so going backwards, if you're starting here and you want to go backwards, we have to notice that, hey, look, it's just half of that. And from there to there, we go, okay, it's just half of that. That's how we get to that number. Okay, so now that we refresh your memory on this, also remember that this is useful for factoring. So here I was just multiplying everything out. But if we start by giving us something like this, given x squared plus 12x plus 36, and they ask us to factor, well, all we have to do is realize this pattern down here, right? I can see that it fits this form, so I can just factor it. And this is just going to be x plus 6 parentheses squared. Easy. All right, well, what if it was just a little bit more complicated? So now, what if they give you something almost close to that, x squared plus 12x? You're like, okay, similar to that. But instead of having a plus 36, there is some other number there. Any number other than 36 or 0, because that would make it too easy. What if it was close? What if it was just 30 instead of 36? Okay, so the key to this process is to realize this. We're really close. Man, if that was only a 36, we would be happy. So the process of completing the square is to introduce the perfect number, the number that would make it a perfect square. In this case, the 36. So I'm going to just put it in there. So I'm going to come in here and go, well, I need a 36. Life would be great if I had a 36, so I'm just going to stick it in there, plus 36. Now, you can't just go around adding 36, that changes the equation. So if I add a 36, I also have to subtract a 36. And then there's this 30 that was already there, plus 30, right? So I just kind of squeezed in between here and added a new version of 0, right? Because these two things, they add up to 0. So I just stuck a plus 0 in the center of that. And you can always add 0 to anything. It doesn't change the value of your statement. So I did a plus 0 there, and then I rewrote that 0 as a 36 and a minus 36. And what's great there is that now the first three terms are guaranteed to be a nice, perfect square trinomial, right? And that, in fact, they fit this form. So now I can rewrite the first three as x plus 6 parentheses squared. So I was able to factor those three. And now I just deal with whatever constant is remaining. So there's a minus 36 plus 30. So these two combined to just give me a minus 6. Minus 6. And there you go. So we didn't completely factor it out. It's not as nice as just factoring the polynomial, but we did sort of a partial factorization here. And that is enough to help us solve many of our questions. So this is the process of completing the square. Figuring out or realizing that we're close to a perfect square trinomial if we only added the perfect thing. And really the only tricky part of this is what to add. Here, I had these equations right over here on the left, so it's easy to spot it. But if it's just some other random equation that's given to you, it might not be as easy. So you got to follow that formula. And that's when it pays off to realize that if you're given something in this form, then in order to figure out the perfect thing to add or subtract, is to take the constant in front of the x. Right? The key is to focus in the constants in front of the x term and divide them by 2. When you divide them by 2, you get to this number. And then once you get to this number, then you know that if you square that number, take this number and you square it, you get to that number. Right? Notice that this is the 12. And then you divide that by 2, that gets you to 6. And then you square that, and that's the perfect number that you need to add. So add and subtract the 12 divided by 2, 6, squared 36. That's how I know to do this value right in here. Good. So another quick example. How about this one? What if I was given x squared plus 8x plus 23? Again, close to this. If that was only a 16, everything would work out really well, but it's not a 16. But we can do a partial factorization by realizing that we can add and subtract the perfect number, right? We can say that this is equal to x squared plus 8x plus 0 plus 23. And now it's all about figuring out how to rewrite that 0, a plus minus the perfect number. And then again, the pattern is to realize that if we focus on this number, if we half that number, we get to the 4. And if we square that number, we get to the 16, which is the number we need to do. Okay, so we're going to focus on this thing. We want to add and subtract. Add and subtract. 8 divided by 2 squared, which is going to be 16. Good. So now we take this, and this gives us x squared plus 8x plus 16. Oh, let me put it in green. This becomes plus 16 minus 16 plus 23. Plus 23, right? Again, this plus 16 minus 16 is really just a 0. It doesn't change the equation. But the advantage is now that we can combine these terms. The first 3 terms are perfect square trinomial. In fact, they are right here. So then the first 3 are perfect square trinomial, and they factor out just like over here. This becomes an x plus 4 squared. By the way, when the numbers get very difficult, it's not quite as easy to spot what it is, but just remember that this number, before you squared it, is the value that goes there. 8 divided by 2. In fact, let me put that on here. Space over here. Come over here and say that this is 4 squared, which is 16. And so the number right there before you squared it is the same number that goes right in here. So when you're dealing with like ugly fractions or decimals and it's not quite as easy to spot it from this form, just remember that it's x plus whatever value is in there before you squared it, including the sign. If this is positive or negative, then this becomes positive or negative. That takes care of the first 3 terms, guaranteed. And now you just deal with whatever is remaining. So whatever is remaining here is going to be a minus 16 plus 23. So that's going to be equal to plus 7. And there you go. That would be our, and there you go. That would be how we use complete the square to rewrite this into this form, right? Notice, by the way, that this is now in vertex form. We go back to the definition of quadratics. This one fits the standard form. standard form. And now this fits the vertex form. Vertex form, right? Where -4 is the h and k is a 7. There's an a out in front, which is a 1, right? So the vertex form is a parentheses x minus h squared plus k. So here a equals to 1, this invisible 1 right in there. We have to have a minus in our vertex form, so that means that this must be a -4, because subtraction of a negative makes it +4. So h is equal to -4, and k equals to 7. Right? Whereas over here in the standard form of a quadratic was ax squared plus bx plus c. Right? And so in this case, the a was a 1. A was a 1. The b is an 8. B is an 8. And the c is a 23. Good. Notice that in both cases, the a stays the same. A is the same. It's a 1. It's a 1. That's always going to be the case. But the other two numbers, they change. Here, there's a constant of an 8 and a constant of a 23. Here's a constant of a -4 and a constant of a 7. So they're a little bit different. And again, the advantage of this form is that now we can easily tell what the vertex is. The vertex is going to be equal to negative. So the vertex is going to be equal to -4, 7. Okay, let's do a couple more examples. Okay, first example. Find all real solutions to this equation. All right. So first we try and factor it. Find two numbers that multiply to 13 but add the 8. Okay, so maybe you'd think, okay, how about x? X, first thing I do, figure out if it factors. Two numbers that multiply to 13. Well, 13 is a prime number. The only way to get to it is 13 and 1. And that does not up to 8 or -8. So that's just not going to work out, right? So pretty quickly, I think we run into a roadblock with that process. So we think about completing a square. So, right, so remember the pattern. We want to add and subtract the perfect number, right? So we take that value right there and divide it by 2. Oh, by the way, I didn't point out, maybe I should have pointed out, that this whole process, let's go back to over here. Notice that this entire process always hinged on having a form of x plus a constant, x plus 2, x plus 3, x plus 4. So therefore, when you FOIL that all out, you always ended up with a 1x squared in every single case. So this process, as we've explained it so far, only works for having a 1 in front of the x squared. When there's something other than a 1, then we have to do one more special little thing first. We'll look at an example like that soon. But for now, notice that that's all I've been working with. And that works out well here as well because there's a 1 right there. So again, we'll look at a more complicated example soon where maybe there's something other than a 1. Okay, so the process is to add a 0, right? So the perfect 0. So let me copy this down. We're going to do x squared minus 8x, and then we're going to add the perfect 0 to this statement so we can complete the square, and that'll help us solve this thing. All right, the perfect 0, right? Following our formula, we focus on this -8, and our formula tells us to add and subtract. The -8, carry the sign, divided by 2 squared, which is going to be -4 parentheses squared, which is equal to 16. Okay, so we add and subtract 16. So now we come back over here. X squared minus 8x, and then I'm going to add a 16 plus 16 minus 16. We always put it in this order, plus, minus, and then keep the 13 plus 13 equals to 0. And now I'm guaranteed with this process that the first 3 terms are going to be a perfect square trinomial, and they will factor into the form x And then the number that goes here is the number before you squared it, including the sign. So I can tell that that's a minus 4 parentheses squared. That's what this will be. And then, of course, you just deal with what remains. So there's a minus 16 plus 13 remaining. So this would be a minus 3 out here. So now we've gotten it into vertex form. Vertex form, where A is 1 and H is 4 and the K is negative 3. Right, so I can tell right there, right away, that the vertex is 4 comma negative 3. It's not what they asked me for, but I can tell some information from it, right? They did ask me to solve it, right? So I have to figure out what x values make this a true statement. So I need to figure out what x values give me a 0 when I replace them there. And this vertex form is very useful for that as well. So I'm going to come back over here now. So I'm going to copy x minus 4 parentheses squared minus 3 equals to 0. And now I can add 3 to both sides, plus 3, plus 3. And I end up with x minus 4 parentheses squared equals to 3. And now I can take the square root of both sides. X minus 4 parentheses squared equals to 3. So I'm going to take the square root of this side. And remember, when we take the even root of both sides, we have to introduce a plus or minus. So there's a plus or minus 3. This results in x minus 4 equals to plus or minus root 3. And then finally, I add 4 to both sides, plus 4, plus 4. And so we get our two solutions. X equals to 4 plus or minus square root of 3. Right? So one solution is x, x equals to 4 plus root 3. And another solution is x equals to 4 minus root 3. Good. So both of these should give us a true statement. Let's check it. Right? Again, if we go back to our original statement and replace x with each of these values, I should get a true statement. So let's check. Blank squared minus 8 times blank plus 13 should be 0. So the first blank I want to check is when x equals to 4 plus root 3. So this would be 4 plus root 3 squared minus 8 times 4 plus root 3. All right, let's see if that works out. Okay, so here I'm going to FOIL this. So I'll end up with 16 plus 2 times 4 times root 3 plus root 3 squared, which is a 3. Then I'm going to distribute here. We get a minus 32 minus 8 root 3 plus 13 equals 0. So this becomes 16 plus 8 root 3 plus 3 minus 32 minus 8 root 3 plus 13. So the roots cancel. That's good because this guy and this guy cancel. And so we end up with 16 plus 3. That makes it 19. 19 plus 13 gets you to 32. Minus 32 does in fact equal to 0. Equal to 0. True. We end up with 32 minus 32, which equals 0. Yes, works out. Good, good, good. And likewise, if we tried a subtraction there, a little minus, it'll also work out. Let's check it over here. Okay, so this is the case when x equals to 4 minus root 3. 4 minus root 3. X equals to 4 minus root 3 case. Okay, so let's FOIL this out. We end up with 16 minus 8 root 3 plus 3 minus 32 minus 8 root 3 plus 13 equals 0. Oh, sorry. This minus 8 becomes minus 32. And then minus 8 times minus root 3 becomes plus 8 root 3. And that's how these guys cancel. Minus 8 root 3 plus 8 root 3. And now we end up with 16 plus 3 gets you to 19. 19 plus 13 is still 32. We still end up with 32 minus 32, and that does in fact equal to 0. So we were able to confirm that these two really do represent both solutions. Okay, here's your author's solution for this one. Pretty much the same thing, a little neater, a little cleaner. Your author chose to do it slightly differently. First thing they did was move this 13 over to the other side, right? So subtract minus 13 minus 13. And then what your author did was trying to take advantage of this equal sign and add 16 to both sides. I like to keep it to one side and add and subtract. That way you don't really change it. So I like to add a special form of 0, whereas the other way to do this is to just add 16 to both sides. Either way works. Okay, and so yes, the same pattern. Take the minus 8 divided by 2 squared. That's how you knew to do the 16. And then you can factor the left-hand side, take the square root, and then we end up with this guy. And again, you can check both answers work out. Okay, here's another example. All right, now in this example, notice that the first thing that comes to mind is that this guy is not a 1. It's something other than a 1. So we might want to try and factor it, see if it factors nicely. This would be the AC method. So if we remember the AC method, step number 1 would be to multiply 3 times 6, the A times the C, which is 18. Step 2 is to find two numbers that multiply to 18 but add the 12. So 3 times 6, for example, work out. They multiply to 18, but they don't add up to 12. 2 and 9, 2 times 9 gives you 18. But they add up to like 11, not 12. That doesn't work out. Of course, 18 and 1 give you 18, but they add up to like 19, or subtract to 7, subtract to 17. These subtract to 7. Yeah, so nothing comes to mind. So there isn't really a good way to factor these. That's how we know that there isn't really a good way to factor these, because I can't find two numbers that multiply to 18, but at the same time add to negative 12. So we kind of give up on the factoring idea and maybe think about completing the square. Now, if you're going to complete the square and there's something other than a 1 there, what you want to do is factor out that value from all of the terms. Now, it just so happens that this last constant is also divisible by 3. So this one's a little easier than normal. So I'm just going to ignore that because that's not always the case. So the general process is going to be to factor it out of the first two terms. Even if it results in a fraction for the second term, you just got to have a 1 right there. So I'm going to factor out a 3, giving me an x squared minus 4x here. And I'm just going to leave that plus 6 out there. Okay, 3 times x squared gives you 3x squared, and 3 times negative 4x gives you minus 12. Okay, and so now I can just focus on this part in here. This part in here does have a 1, so I can just use my normal complete the square process in order to figure out how to do that partial factorization of this guy. Okay, so I'm going to add and subtract the perfect number, and the perfect number, again, is this. Add and subtract the negative 4 divided by 2 squared, which is equal to negative 2 squared, which is equal to 4. So this thing is telling me that the perfect thing to add is a 4. So I'm going to come in here and I'm going to add a perfect 0, x squared minus 4x plus 0, the perfect 0, plus 6 equals to 0. And now this perfect 0 is plus 4 minus 4. So this would be 3 parentheses x squared minus 4x. The perfect 0 is plus 4 minus 4. Close that. Plus 6 equals to 0. Good. Now I'm guaranteed that the first 3 terms right here are going to be a perfect square trinomial. So that's going to be a x minus 2 coming back to over here, it's the number before I squared it. That's what goes right in here. Okay, and that gets squared. There's still a minus 4 there. The whole thing is still being multiplied by this 3 on the outside. And there's still a plus 6 out there. Good. But now I can just easily distribute this 3 there and there. Not there, right? The 3 only multiplies to these values, not the 6. Okay, so that reduces to 3 parentheses x minus 2 parentheses squared minus 12 plus 6 equals to 0. And now I can combine these two terms to get me to 3x minus 2 squared minus 6 equals 0. Okay, and so now we've gotten into vertex form. This is the standard form. Standard form. ax squared plus bx plus c, right? And this is where the a was being played by a 3, the b was being played by a negative 12, and the c was being played by a 6, and we're setting that equal to 0. Good. And then we did all of this work over here, and we got it to vertex form. Vertex form. ax minus h squared plus k equal to 0. Good. And that's where the a is being played by a 3, the h is being played by a 2, and the k is being played by a minus 6. A, h, okay? And so because it's in the vertex form, they didn't ask us for this, but it's a useful thing to know. The vertex is going to be at 2 comma negative 6. 2 comma negative 6. It's at h comma k. H comma k is the vertex. Okay, so we got it into vertex form, and once we have it into vertex form, one of the advantages of the vertex form, besides being able to tell the vertex really easily, is that you can solve for x really easily as well. So let's copy it back up here. So we ended up with 3x minus 2 squared minus 6 equals to 0. To solve this guy, I'm going to add 6 plus 6 plus 6. So I end up with 3x minus 2 squared equals to 6. Divide both sides by 3, or multiply by a third. So 1/3 times 1/3 gets me 2x minus 2 parentheses squared equals to 2. And now I take the square root of both sides. And so x minus 2 squared equals to 2. I'm going to take the square root of this side, square root, and the square root. It's an even root that I introduced, so I have to throw in the plus and minus, two possible solutions. And now I can take x minus 2 equals to plus or minus root 2. And now I just add 2 to both sides. So plus 2, and so we get our solutions are x equals to 2 plus or minus root 2, right? So this gives us two solutions. Either the x is a 2 plus a root 2, or x equals to 2 minus root 2. Two perfectly good solutions. Okay, let's check them over here. So if they work out, if they're true, then that means if we go back to the original statement, we can replace the x by either one of these and get a true statement. So it should be true that 3 parentheses squared minus 12 parentheses plus 6 equals 0. So let's just put in the 2 plus root 2 and a 2 plus root 2 in there. Let me zoom in. Okay, so to simplify this, we're going to FOIL this guy. That'll give us 3 parentheses. That'll be 4 plus 4 root 2 plus 2 minus 24 minus 12 root 2 plus 6 equals 0. Distributing the 3, we get 12 plus 12 root 2 plus 6 minus 24 minus 12 root 2 plus 6 equals 0. So then the plus 12 root 2 and the minus 12 root 2 cancel out, and we end up with a 12 plus a 6 plus another 6. That'll give us positive 24. So we'll end up with 24 minus 24, which does in fact equal to 0. It does work out. Okay, so now let's check the other one. That's 3 parentheses blank minus 12 parentheses plus 6 better be a 0. And we're thinking that the answer could be 2 minus root 2. 2 minus root 2. Okay, so if we FOIL this out, we end up with 3 parentheses 4 minus 4 root 2 plus 2 minus 24 plus 12 root 2 plus 6. Hopefully that equals 0. Distributing the 3, we get 12 minus 12 root 2 plus 6 minus 24 plus 12 root 2 plus 6 equals 0. And now the minus 12 root 2 and the plus 12 root 2 cancel out, leaving you a 12 plus a 6 plus a 6. That gives you 24. So that gives you 24 minus 24, which does equal 0. So again, it worked out. So both solutions do work out. This was, let's organize this. This was for the case of x equals to 2 plus root 2. So over here, this is the case of x equals to 2 minus root 2. Okay, so there you go. We started with a polynomial in standard form. We're asked to solve it, figure out what values of x give you a true statement when it equals to 0 like that. So then we did the complete the square process to rewrite it into the vertex form. From the vertex form, obviously we can tell the vertex, which is very useful, but not what they asked us for in this case. But the other nice thing is that we can solve for 0 quite nicely once it's in the vertex form. So we get to set it equal to 0. So we add 3, divide by 3. I'm sorry, add 6 to both sides, divide by 3, take the square root, and there you go. Okay, the quadratic formula. So the quadratic formula is a formula that is derived by solving exactly what we just did in general, so that we can come up with a general formula instead of applying the complete the square process. So what I'm going to do to derive the quadratic formula is do exactly what we just did, complete the square, on something that fits this form. Right? So just a second ago we did something just like it, so we're just going to follow the same little recipe. So we're going to do ax squared plus bx plus c equals to 0. This is where, keep your eye, there's a lot of letters running around, but the a, the b, and the c represent constants, right? So maybe in your head, think of it as 3x squared plus 2x plus 7 equals to 0, right? So the a, the b, and the c represent numbers. So treat them as numbers. We can factor them, add them, divide them as numbers. Just keep in mind that the only thing we really know for sure is the a cannot be a 0, right? That's because if it was a 0, if the leading number in front of the x squared was a 0, well then this whole thing would be 0, and then this whole thing would be 0, and then we wouldn't have a quadratic anymore. We would only have a linear equation. So it just prevents us from overly simplifying the statement. Okay, so if you remember the complete the square process, the first thing we have to do is make sure we have a 1 there by factoring out the first 2 terms. That's what we did before. So I'm going to factor out an a. So the first one is easy because a times x squared, well, that's easy. That's just x squared there. The second one is tough because, well, I don't really know what the numbers are, so I'm not even sure if a is a factor of b. But one little trick to do this is to rewrite it as a fraction. If we write it as a b over a, then a times b over a, the a's cancel, giving you b. So it factors like that. And then we leave the c alone, plus c equals to 0. Okay, so now Now we have a 1 here. That's what we needed, right? It was important to note that the complete the square process only works as long as there is a 1 right in front. And then we follow the little formula. We need to add the perfect number, the perfect 0. So I'm going to copy this down here. Ax squared plus b over ax. And this is where I add my 0. The perfect 0 needs to go there. Plus a c equal to 0. And now the formula says that I focus on the number, the constant, in front of the x. Just like before, we got to take this number. So the perfect thing to add is to add and subtract the b over a times 1/2. It's half of it. Half of that number squared is the perfect thing to add and subtract. So simplifying this a little bit, this is just going to be b squared over 4a squared. That's the perfect value to add and subtract to guarantee a perfect square trinomial. So now I copy this down over here. I get x squared plus b over ax. And the perfect thing to add and subtract is b squared over 4a squared minus b squared over 4a squared. Close parentheses plus c. All right, let's look at the previous one now, just to make sure that we're following the same template. Okay, so if I remind you of what we did before, we started by factoring out this 3. Now in this case, they're numbers. I can tell that 3 and 12 factor nicely. But the other thing I could have done is rewritten this as a 12 divided by 3, which is also going to work out. Okay, so then we want to add and subtract the perfect number right here. And the perfect number comes by taking the constant in front of the x, multiplying it by 1/2, and then squaring it. For us, the constant in front of the x is the b divided by a. So b divided by a times 1/2 is the same thing as this little step right here. And then we square it, and that's what we get here. We add and subtract the perfect number. Good. Next, we guaranteed that the first 3 are perfect square trinomials. And the number that goes in here is really this number before we square it. That's how we get this value right in here. So let's go back. Okay, so now we're guaranteed that the first 3 are perfect square trinomial and that they factor as an x plus this value, the value before you squared it, which was equal to b over 2a squared, right? That's the value before you squared it. That's what goes there. And there's still a minus b squared over 4a squared term there. The whole thing still being multiplied by a, and there's still a plus c out there. Good. Oh, I lost my 0. Equals 0 equals 0. Okay, next we're going to distribute this a like this and like that. And so I'll end up with a parentheses and then x plus b over 2a parentheses squared minus a times b squared over 4a squared. And there's still this plus c and a 0 out there. Simplifying things just a little bit here, this a and this a reduce. So I'm going to get an a parentheses x plus b over 2a close parentheses minus b squared. And I'm going to rewrite this as an addition of a negative b squared over 4a. Remember, the square only applies to the b, not the minus. So this is not just positive. So it's a negative parentheses b squared plus c. And then kind of thinking ahead, I'm going to combine these fractions. So I'm going to multiply it by a 4a over 4a so that these two have a common denominator of 4a. And then I can combine them into one big happy fraction. I'm going to do that right here. So this would be ax plus b over 2a squared. And this is going to be one big happy fraction where I have this minus b squared plus 4ac divided by 4a plus equals to 0. Okay, and so this is the vertex form. It's really ugly, but it's the vertex form. Let me zoom out. So this fits the vertex form, right? Remember the vertex form was ax minus h squared plus k equal to 0. Well, this crazy weird thing over here, there's no x's there. They're all numbers, right? So this whole thing represents the k, and then the b over 2a, well, minus b over 2a is equal to h. Let's write it that way. Minus, that way they turn into a plus like before. And so now minus b over 2a represents the h. And so it's in the vertex form, right? So again, from the vertex form, I know that h comma k is the vertex. So from here, I can tell that negative b over 2a comma this crazy thing minus b squared plus 4ac divided by 4a, that this is our vertex. That'll become useful later on. Good. And for now, we can move on to the process of solving it. And so remember, for solving it, this is some constant. We move it over, divide by the a, take the square root of both sides, and then you can solve for x that way. So let's keep going with the process of solving it. So this, subtracting this whole highlighted yellow thing on the other side, we end up with a parentheses x plus b over 2a parentheses equals to negative, and this is negative b squared plus 4ac all over 4a, right? Subtraction, I took this whole thing and subtracted it, right? Because this is a plus here. I'm going to multiply both sides now by 1 over a, and then multiply this whole thing by 1 over a. Remember, we were told that a is not 0, so we're okay doing this. We have to be careful to make sure that we don't accidentally divide by 0. Okay, on the left-hand side, the a's cancel, giving me an x plus b over 2a close parentheses squared equals to, now I'm going to go ahead and distribute this minus here, right? This minus kind of represents a minus 1. This is a minus 1 times all that. So I'm going to distribute that, and I'll end up with a positive b squared minus 4ac. Might start to look familiar now. And then in the denominator, I'm going to multiply those, so I end up with a 4a squared. Good. In the process of solving, now I want to take the square root of both sides. So I'm going to take the square root of this side, the square root of this side. Whenever you take the square root, you have to introduce the plus or minus. Plus or minus. So now we end up with x plus b over 2a equals to plus or minus, and I'm going to separate this root, the root of the numerator, the root of the denominator. So this is plus or minus b squared minus 4ac, starting to look familiar maybe, divided by, and then the square root of 4a squared. Okay, almost there. Now I just have to subtract this fraction to both sides. So we get that x equals to minus b over 2a plus or minus the square root of b squared minus 4ac divided by, and the square root of 4a squared, this is just going to be 2a. So I'm going to rewrite that as a 2a. And now luckily, both fractions have the same denominator, so we can just rewrite this as x equals to negative b plus or minus the square root of b squared minus 4ac divided by 2a. And there it is. This is our quadratic formula. It might look familiar, right? And so let's zoom out and look at the whole thing. All right, a lot to take in. So we started with something that, again, fit the standard form of a polynomial, like a polynomial equation, right? So here, this fits the standard form. Standard form. So similar to before when we actually had some numbers in there, we followed the process of completing the square. Factor out an a, right? This little trick right here works to get this fraction to factor it. A times 1 equals a times b over a gives you b. Leave the c alone. Then we have this little fraction in there, so we want to work with that guy to figure out the perfect thing to add and subtract. Because we have a 1, now we've put a 1 in front of the x squared, the perfect thing to add and subtract is going to be half of this squared. And that'll give us the perfect value, right? So this complicated looking fraction here, remember there's no x in there, all these are constants, so this represents some number. Once you know the value of b and a, you can plug them into this little formula, get some number, and that's the perfect thing to add and subtract. Then the process of completing the square guarantees that the first 3 terms are perfect square trinomial, right? So this is where we kind of have to lean on the process, rely on it, and know that it gives us what we're looking for. So the first 3 are going to factor this way: x plus b over 2a, right? This b over 2a is the number that was over here before we squared it. That's what goes there, squared, minus, and then we bring down the minus b squared over 4a squared. Distribute the a, reduce, right? Then we get a common denominator, combine, we get this guy, and then we can we've achieved the vertex form of a quadratic. This is x minus h squared times a plus some constant k equals 0, right? So that's the vertex form. So therefore the vertex will be equal to this minus this, right? Extra information, we don't need it yet, but that'll be useful soon. For now, we can keep moving and solve for x. So remember, this is just one giant number, so we subtract this fraction from both sides of the equal sign. And so that's how we get a minus 1 here. Then we multiply both sides by a 1 over a. That'll cancel with this a. Then we take the square root. It's an even root, so we introduce the plus or minus to get this. Simplify it a little bit, and before you know it, here it is. So this hopefully looks kind of familiar, the quadratic formula. So remember what we've accomplished. This formula is useful when you're given something of this form. If you're given a quadratic in standard form, ax squared plus bx plus c equals to 0, and you need to figure out what values of x make this a true statement. What values of x will result in the left side equaling 0, just like the right-hand side. Then, well, you can just use this formula. It's negative b plus or minus the square root of b squared minus 4ac divided by 2a, right? And the a, the b, and the c refer to these constants that are right in front of here, right? So it's just a shortcut, so you don't have to repeat the complete the square process every time. We've done it in general, and now we have a nice little formula for it. Okay, so in terms of the homework in the exam, pay attention to the instructions. If the instructions say to use complete the square, then you're not allowed to use the quadratic formula. You have to do the complete the square process. If the instructions say use the formula, obviously use the formula. If they don't have any information, then you get to do whatever you want. So if you want to complete the square, that's good. Or if you want to just go ahead and use the quadratic formula, that's fine. As far as my test is concerned, again, pay attention to the instructions. I will definitely have at least one question where you're asked to use the complete the square process, but there might all be also other questions where I don't specify it, and therefore it's kind of up to you. Okay, so here's just the presentation of the quadratic formula. So the roots of the quadratic formula, remember the roots are the values of x that make this a true statement, that make this the left-hand side equal to 0. The roots are found by using this formula. The answers will be x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so let's look at some examples where we use this formula to solve for roots. Okay, let's tackle these three questions. Find all real roots in each case. All right, so for the first one, we have 3x squared minus 5x minus 1 equals to 0. Okay, so this fits the form of ax plus b. Fits form of ax squared plus bx plus c equals to 0, where the a is equal to 3, the b is equal to minus 5, and the c equals to negative 1. So then when we apply it to our quadratic formula, we get negative b, where b itself is a negative number, so I'm just going to leave it like this, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. All right, so let me plug these values in. So negative b, where b is already a minus 5, plus or minus the square root of b squared, so that's going to be minus 5 in here squared, minus 4 times a times c, which is also a minus 1. And the whole thing is divided by 2 times a, which in this case is a 3. Okay, so now we just simplify this, and we get that this is going to be 5 plus or minus the square root of 25 minus 12, negative 12, so plus 12. Since we have a minus here and a minus there, plus 12 divided by 6. So x equals to 5 plus or minus the square root of, that's going to be 37 over 6. And the root of 37 doesn't really simplify, so we just leave it like this. There are two possible answers. X equals to 5 over 6 plus 1/6 root 37 is another way of writing it. Or x equals to 5 over 6 minus root 37 over 6. Good. Two possible answers. Since it's a root, you can either plug it into the original equation and check it, or you can turn it into a decimal and then again plug it into the original equation and check it there. Here's the solution from your author. So again, recognizing the a, the b, and the c, you simply just plug it into your quadratic formula, and then you can reduce it, simplify it, right? So an exact answer would be this one. Again, pay attention to the instructions. If it says write down the exact answer, you would write it like this. If in fact it says that you're allowed to turn it into a decimal and round, then you do this. For me on the test, by default, always leave things as a complete answer unless I specifically say you're allowed to use a calculator to reduce it. Okay, so if you're given permission to use a calculator to reduce it, then you can reduce it this way, convert it into a decimal. Either way, in order to just kind of confirm for yourself that this is true, what you would like to do is take this decimal, plug it right in here, use a calculator, and figure out that hopefully it does in fact give you a true statement. So if it's a true statement, 3 blank squared minus 5 times blank minus 5 equals to 0, you should be able to come in here and plug in a 1.8471 and a 1.8471. And this should give you a true statement. On the other hand, if you also plug in negative 0.1805 and negative 0.1805, that should also give you a true statement. Keep in mind that this is a rounded value, so this won't exactly be equal to 0, but pretty close, enough to convince you that you have a good answer. Okay, now let's take a look at the second one. We have 4x squared plus 12x plus 9 equal to 0. And now this fits the form where a equals to 4, b equals to 12, and c equals to 9. So we use our quadratic formula and say that x must be equal to negative 12 plus or minus the square root of 12 squared minus 4 times 4 times 9 2 times 4. And then we go ahead and simplify it. So this becomes x is equal to negative 12 plus or minus the square root of, and 12 squared is 144, and minus 4 times 4 times 9, that's going to be 16 times 9, which is 144 as well, divided by 8. So now the 144 minus 144 reduce. So this is a case where the value inside the root becomes 0. So that actually simplifies quite nicely. This becomes the square root of 0 over 8. The square root of 0 is 0, so that term just kind of goes away. And so what we're left with is just x equals to negative 12 over 8, which reduces to negative 3 over 2. So we don't have two answers in this case, we only have one. Okay, and this is the solution from your author. Again, it's just plugging into our formula, just recognizing that the A is a 4, the B is a 12, the C is a 9. Plug it into our quadratic formula, plug and chug away, and simplify, reduce. Again, this is a case where the value inside the root works out to be 0. Square root of 0 is 0, so we're just left with a single answer. Oh, I should be completing this. This is x equals this, x equals that. So here's our answer. Okay, last one. Okay, last one. So this one is x squared plus 2x plus 2 equals 0. So again, this fits the form. Fits the form of ax squared plus bx plus c equals 0, where a is being played by a 1, b is being played by a 2, and c is being played by a 2. So again, if we just apply our quadratic formula, we get negative 2 plus or minus the square root of b squared, which is going to be 2 squared, minus 4 times a times c, all over twice a, which is a 1. Okay, so reducing this, we get negative 2 plus or minus the square root of 4 minus 8 all over 2, and then we see that there's a problem here. We end up with x equals to minus 2 plus or minus the square root of minus 4 all over 2, and so we see that this is going to be the even root of a negative number. This is going to lead to a imaginary or a complex number, right? Which we haven't talked about yet. We'll get to them soon. But for now, it's not a real number, right? So no real number solution. No real number solution. No real number solution. Right? So we'll get to the imaginary soon, or complex numbers. But for now, we just stop and say there's no real number solution. By default, if something asks you to find a solution, by default, we know that they're looking for the real numbers. But in this particular case, it in fact said find all real solutions. So, pay attention to the instructions. Okay, so here's your author's solution for this question. Same thing, just find the values of a, b, and c, plug them into your quadratic formula, and then he simplified it just a little bit further than I did, but that's okay. So this is x equals that, x equals to that. So then this simplifies this way. I just kind of stopped here and realized at this point that there was going to be no real number solutions, so I stopped there. But you can simplify it a little bit more. So you can factor out the 4. Right, so from here, I'll put it over here. Root negative 4 is equal to root negative 1 times positive 4, which is equal to root negative 1 times root 4, which is equal to root negative 1 times 2. And now the root -1 is equal to I, which we'll get to in a little bit. But at any rate, this is where we realize that we have an imaginary solution right in here. Right? This is what we're going to later on define to be an imaginary number. But for now, we just stop there and say there are no real number solutions. So the discriminant. The discriminant refers to the little equation that's inside the root of the quadratic equation. So the b squared minus 4ac. Notice that in the three examples that we saw above, we had three different cases. One of them was the case where the discriminant part, this part, turned out to be a number that was greater than 0. Therefore, we ended up with like a root 37 in that case. And we had plus or minus root 37. We ended up with two solutions. So if that value, if that discriminant is greater than 0, then the equation has two distinct real solutions. That's this case. If the discriminant part is greater than 0, then it has two distinct real solutions. On the other hand, there was a case where the thing inside the root, discriminant, equaled to 0. And so if it equaled to 0, that whole root becomes square root of 0. And so we have plus or minus 0. Therefore, we only have one real solution. Only one real solution. We saw that example as well. Let's put this one in green. So if d equals to 0, the discriminant equals to 0, there's only one real solution. If it's greater than 0, then it has two distinct solutions. On the other hand, as we saw in the third example, if the d value, if the discriminant is negative, then we end up with the square root of a negative number, which is undefined. So if the discriminant is less than 0, if it's negative, then the quadratic has no real solutions. No real solutions. So we can use that little fact to simplify things a little bit sometimes. We may not want to find an answer sometimes. Maybe we just want to know if an answer exists, right? Maybe it's just a binary question. Is there a solution, yes or no? So we can check by looking at the discriminant and determining if that value is going to have no solutions, one solution, or two solutions, right? Real number solutions. So organizing all that, we get this. The discriminant of a quadratic equation, ax squared plus bx plus c equals to 0, where a doesn't equal to 0, is given as b squared minus 4ac. Again, just the little part inside the radical, inside the root of the quadratic formula. And we have three different cases. If that d value is greater than 0, strictly greater than 0, then we know we can expect two real solutions. If that d value equals to 0, then we can expect exactly one real solution. And if that d value is less than 0, it's a negative number, then we expect no real number solutions. There is imaginary solutions, by the way, but not real number solutions. For example, let's say we just wanted to know how many real solutions each of these equations had. So remember, we're not necessarily interested in knowing what the answer is. We just want to know if it has 0 solutions, 1 solution, or 2 solutions. So to figure that out, we can just calculate the little d value, the discriminant value. So for the first one, we just have to identify it as a quadratic where the a value is 1, the b value is 4, and the c value is -1. And then we just plug it into our little formula, b squared minus 4ac. In this case, we get that it's equal to 20, which is greater than 0. So that tells me that there's going to be two real number solutions to this equation. For the next one, we have 4x squared minus 12x plus 9 equals to 0. So again, this fits the standard form of a quadratic where a is equal to 4, b is equal to -12, and c is equal to 9. Again, we just plug it into our little formula for the discriminant, and we get -12 squared minus 4 times 9 times 4, which gives us 0, just like in the example above. And so therefore, we can expect only one real number solution to exist. Again, we didn't really find the solution, we just know that there's going to be one solution. Finally, if we have 1/3 x squared minus 2 plus 4, the a value is 1/3, the b value is -2, the c value is 4. Plugging it into our formula, we get -2 squared minus 4 times 1/3 times 4, which gives you a -4/3. It's a negative number. We know that we can expect no real number solutions in this case. Okay, modeling with quadratic equations, right? So modeling with quadratic equations, that just means that we're gonna find some real world word problems to work out in our equation. Okay, a rectangular building lot is 8 feet longer than it is wide and has an area of 2,900 square feet. Find the dimensions of the lot. All right, so always read your word problems once, twice, 3 times. Make sure that you have a pretty good idea of what they're giving you, what they're asking. Maybe draw a little picture, a little sketch with the information provided. So this is a rectangular building lot. It's pretty straightforward. So there's some sort of rectangular lot. Okay, so we have some sort of rectangular lot. And so one of them is the length, one of them is the width. It doesn't matter which is which, as long as you're clear with your notation. So I'm going to call this one my length, call this one my width. Okay, so the rectangular lot is 8 feet longer than it is wide. So it kind of matches my picture. The L is longer than the W. Find the dimensions of the lot. Okay, so with word problems, you want to use as few letters as possible. Whenever you can sort of recycle a variable, you're going to get a simplified equation. And so we want to use the idea that L is 8 feet longer than W. So the W is smaller. If I add plus 8 to it, it should get me to my L. Right? Because thinking about it this way, the L is already shorter. I got to add 8 to it, and that's how I get to this one. So a very common mistake is for people to do this. Right? And hopefully it's clear why this one can't be true. Right? The L is already the longest one, and you want to add 8 to it to make it equal to the shortest one. So that doesn't make any sense, right? Okay, so we have a way of describing L. L is equal to W plus 8. And now we want to use the equation for the area of a rectangle. The area of a rectangle is just L times W. So we get that A for area is equal to L times W, but L we said was equal to W plus 8 times W, and we know that the area is 2,900, right? So we get that 2,900 is equal to W plus 8 times W. So now we want to solve this. Okay, so this is a quadratic, because if I distribute this W, I'll get a power 2. So let's turn it into a quadratic in standard form. So I'm going to distribute the W squared plus 8W, and then move everything to one side. So I'm going to move this to over here, and I'll end up with 0 equals to W squared plus 8W minus 2,900. Good, and now I want to factor this guy. So let's see if it factors easily. It's a trinomial, leading term is 1. So let's try this. So now I have to think, are there two numbers that multiply to 2,900 but add to 8? That might be kind of hard to figure out. Let's find the factorization tree of 2,900. So clearly 29 times 100 works. 2,900. 29 is a prime number, so this becomes 2 and 50, 2 and 25, and 5 times 5. Okay, so 2,900 has the factorization of 2 squared times 5 squared times 29. So there aren't too many combinations that could work. I want two numbers to multiply to this negative number, but add to 8. So both numbers have to be kind of close to each other. In other words, if I lean too much on one of them, it won't work. So just kind of playing around with it. How about if I rearrange it this way? I'm going to put the 2 and the 5 squared in one pile, and I'm going to put the other 2 in the other pile. Oops. And I'll do it this way, just kind of playing around with it. And I get 50 times 2 is 50. I'm sorry, 25 times 2 is 50 times, and then this one's 58. So 50 times 58 equals to 2900, and that's going to give me a gap of 8 that I need. Okay, so I'm going to put a 58 here and a 50 here. I need it to be positive, so I'm going to put a plus there and a minus there. Okay, so they multiply to negative 2900, but add the positive 8. Good. Okay, and so now we've accomplished rewriting our quadratic by factoring it, and now we can use the zero product property. Remember, when a times b equals to 0, that means that either a is 0 or b is 0. So I can separate this into the two cases. W plus 58 must be 0 is one case, or w minus 50 equals to 0 is another case. From here, we get that w equals to negative 58. And from here, we get that w equals to positive 50. Now, going back to our word problem, w represents the width of this lot. And the width of a lot cannot be equal to a negative number. So we can just kind of eliminate that possibility. Good. So the only thing that survives is this one. That one must be the case. So that must mean that if w is 50, that must mean that L must be equal to 50 plus 8. Looking at here, W equals to 50 plus 8. So plus 8, which is 58. All right, so we just confirm it, make sure that it's true, that if we multiply 50 times 58, which, well, we already have that over here, it equals to the 2900. And it's true that the length is 8 feet longer than the width. So it makes sense. We found our answers. This side, the L is equal to 58, and this side is equal to 50, and they satisfy the conditions we have. Right? The L, the rectangular lot with the building, so the lot is 8 feet longer. It's 8 feet longer than its width, and the area is equal to 2900. Okay, that was easy. Let's try another one. Okay, the path of a projectile. So an object thrown or fired straight up at initial speed of v0 feet per second will reach a height of h, and will reach a height of h feet after t seconds, where h and t are related by the following formula. Okay, so h equals to negative 16 t squared plus v0 t. Okay, so remember that this v0 right here, this represents initial velocity. So don't let the little subindex confuse you. It's just part of the name of this variable there. So if we know the initial velocity, we can plug it into here, and then we have an equation which tells you the height as a function of time, where time is the number of seconds that have elapsed since the object was initially thrown up. Okay, so now that we have all of that, here's a little picture of it. So you're going to start, presumably you're starting down here. Start. Then you shoot it up. Goes up, 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 up. Right? So we have some initial velocity, but then as we climb up, the object is fighting gravity. It's fighting air friction, right? There's all kinds of things happening. And then it reaches some maximum height. Max height, where it kind of comes to a momentary stop at 0, and then it begins to fall. Okay, so this equation will tell us the height of the object as a function of time, right? So like maybe at 1 second the object was here, and then at 2 seconds the object was there, and so on and so forth, till it reaches some maximum. And this equation will also tell you the height of the object on the way down. So maybe by the time we're way over here, I don't know, I'm just making something up right now. Let's say by the time we're at t equals to 45 seconds, maybe we're already on our way down, for instance. Okay, all right, so suppose that a bullet is shot straight up with an initial speed of 800 feet per second. Okay, so they've given you v0. v0 for this case, a bullet, is equal to 800 feet per second. So that's what goes right in there. So our new equation for this situation of a bullet being shot straight into the air is going to be that the formula is h equals to negative 16 t squared plus 800 t. Okay, so that's the equation we want to use for this situation of a bullet being shot straight up into the air with initial velocity of 800 feet. Okay, so with that in mind, let's answer a few things. When does the bullet fall back down to the ground? When does it reach a height of 6,400? When does it reach a height of 2 miles? How high is the highest point that the bullet reaches? All right, so if I'm kind of visualizing this, okay, you shoot up into the air, okay, probably goes pretty far up, and then eventually will come down, right? Okay, so for the first question, when does the bullet fall back to the ground? Well, using our formula, right, we got that V naught equals to 800. We can plug it right into our equation and get that H equals to negative 16 t squared plus 800 t. Remember that this H, the height value, is the height at both on the way up as well as the way down. It'll tell us the whole path of the bullet in this case. So when does it reach the ground? Well, it reaches the ground when h is equal to 0. So that's what we have to solve here. Let h equal to 0. All right, part A. When does the bullet fall back down to the ground? Okay, so remember the situation. We have a bullet going up. So we start here, say on the ground level. We start here. The bullet goes up to some height, and then eventually wind resistance and gravity will win. It comes to a stop at some point up here somewhere, and then comes back down. And at some other point, it ends there. Either way, remember that the formula that we're using, h equals to negative 16t squared plus 800t, the h is going to be all the way up and all the way down. It's not just on the way up. It'll tell you the height of it all the way throughout the process. So maybe when t equals to 1, the h value will be maybe around here. When t equals to 3, maybe the h value will be around there. I'm not sure. So eventually we'll reach up there, but it also catches it on the way down. Maybe t equals to 16 or something is over here. And so eventually it'll describe it for you. So if we want to find out when does this bullet hit the ground, what we want to do is figure out when is h equal to 0. Right? At the start, h equals to 0, but also at the end, h equals to 0. So we're going to get two answers where it equals to 0. Okay, so we just go back to our equation, let h equal to 0, and solve. So we get to this equation. 0 equals to negative 16 t squared plus 800t. Luckily, that's a really easy one to solve. All we have to do is factor out the negative 16, and we end up 16t, and we end up with negative 16t times t minus 50. And then again, using the zero product principle, either the minus 16t equals to 0 or the t minus 50 equals to 0. And so from there, we get two solutions, at t equals to 0 and at t equals to 50. Good. That means that the bullet went up to the highest point possible and came back down within 50 seconds. At the 50-second mark, it hits the ground. Good. That's kind of surprising to me. I would have thought that would have taken longer, just kind of guessing. I would have thought it'd take longer for it to go up to some high value and come back down. So within 50 seconds, a bullet will come back down and hit the ground. Okay, so when does the bullet back down? So answering the question, when does the bullet fall back to the ground? At t equals to 50 seconds. Okay, part B. When does it reach a height of 6,900 feet? When does it reach a height of 6,900 feet? Okay, so we set our equation, going back to our equation, h equals to negative 16t squared plus 800t. Well, we just set h equal to 1,600 and solve. So we plug in the 1,600. This time it's not 0, so we can't use the zero product principle as we did with part A. So we move everything to one side, and luckily in this case, the 16 factors, everything divides by 16. That simplifies to t squared minus 50t plus 400. And then after a little bit of guessing and checking, we see that this also factors. 400 is equal to 10 times 40. So negative 10 times negative 40 equals to positive 400. And when we add them, they give you a negative 50. Okay, if you're having trouble figuring out two numbers that multiply to 400, try doing the prime factorization of 400 and then kind of playing around with all the possible answers, all the values, all the factors, until you get to the two numbers that work out. Okay, so then this tells us that it will reach 6,400 feet, sorry, at two different time points, at t equals to 10, so 10 seconds, and at 40 seconds. So on the way up, t equals to 10 seconds. So here's 6,900. So on the way up at t equals to 10 seconds, this guy is on its way up. Here it is. It reaches a height of 6,900. That corresponds to this one. And then keeps going, comes back down. On the way down at t equals to 40 seconds, it reaches again the same height, 6,400. Okay, so that's why there's two solutions. At t equals to 10 and at t equals to 40, the bullet will reach 6,400 feet. Okay, part C. When does it reach a height of 2 miles? Okay, so first of all, we have to convert miles into feet because this equation was given in terms of feet. So we can't just plug in a 2 in there. So we have to use a conversion. So 5,280 feet equals 1 mile. So if we double that, we get to 10,560 feet. So what this thing is asking us is to replace h by 10,560 and solve just as before. So we go back to our equation where the h is equal to 10,560. So we get 10,560 equals to negative 16t squared plus 800t. Just like before, we move everything to one side, try and factor it. 16 factors into all three terms. So that simplifies it to t squared minus 50t plus 660 equal to 0. And, you know, maybe you would try and factor it for a little bit, but I think you'd have a hard time trying to figure out if there is a solution. So we can check by looking at our discriminant. So the discriminant of our equation is equal to negative 50 squared minus 4 times 1 times 660, which we see is equal to negative 140. That means that if we use the quadratic formula to solve this, we see that the value inside the root is negative. That's how I know that there are no real number solutions, right? So if the instructions don't tell you to use a discriminant and you're not, it doesn't occur to you, then proceed, right? Try and factor this, and if you can't factor it, then try using the quadratic formula. And when you're using the quadratic formula, you'll run into the discriminant inside the root, and that's when you'll run into a negative. That's when you'll realize that, hey, it's a negative. There are no real number solutions. Thus, this equation has no real number solutions, so the bullet never reaches a height of 2 miles, right? It reaches some other maximum height, which is shorter than the 2-mile mark, didn't quite get that high, and then it came back down. Again, to me, that kind of surprises me. I thought it was going to go higher than 2 miles, and I thought it would take longer than 50 seconds, but that's what it is. It doesn't go as high as 2 miles, and it takes 50 seconds to go up and come down. Okay, so hopefully this is enough to help you finish all your homework. Please come by my office hours if you have any questions.